So I want to do a problem that just involves a slightly more complicated function than the one we used in the past, just to demonstrate different types of critical points. So the problem here is to find and classify all critical points of f, where f is defined in this piecewise way that you see on the screen. When we say find and classify the critical points, what we mean is, first of all, identify them, and second, say whether they're whether they're local mins, local maxes, or neither. And this is a type of problem that comes up for a couple of sections in this course, and then it resurfaces. If you take Calc 3, there are also find and classify problems of this type. So so you figure it was useful to get used to that language at this point. So first of all, recall that for a piecewise function, we can actually differentiate it piecewise as long as we treat the transition points specially. So even though the second definition, the 4 minus 3x, is the definition of the function at x equals 1, we're going to have to be a little careful about what we say about x equals 1, and you'll see why. So here I can say that the derivative of the function is 3x squared for x less than 1. And the derivative of 4 minus 3x is just negative 3. That's for x greater than 1. So what happens at x equals 1? We're fortunate that here these expressions are actually both defined at x equals 1. So at x equals 1, we can say that 3x squared is equal to 3 times 1, which is 3, and negative 3 is equal to just negative 3. So what we can see is that these are not equal. And therefore, since we're getting different tangent slopes depending on whether we approach one from the right or left, what that means is that the tangent slope, the limit that gives us the derivative at that point, must be undefined. So what we can see is that f prime of x does not exist at x equals 1. And as to where it's 0, we can see that it's that negative 3 is never equal to 0. 3x squared is equal to 0 only at x equals 0. So f prime of x equals 0 at x equals 0. So we can see that x equals 0 and 1 are critical points. Okay, so now that we know what the critical points are, let's see whether the derivative is positive or negative, and on which intervals that's true. So let's actually put the critical points 0 and 1 on a number line, and let's ask whether f prime is positive or negative on the intervals negative infinity to 0, 0 to 1, and 1 to positive infinity. So for numbers that are less than 0, we're going to be using this definition of this expression for the derivative. If I square a non-zero negative number, I get a positive number. So 3x squared for any values that are less than 0 is always going to be positive. So we have positive there. And in the interval 0 to 1, if I take a number and square it, I'm going to get a positive number. Multiply it by 3, I'll still get a positive number, so that's going to be positive. And for x greater than 1, the derivative is just a constant of negative 3, which is always a negative number. So what we can see here, just from looking at this sign chart, since I can say straight away that whether the derivative is positive or negative, what I can see is that this is neither a min nor a max. And this point here, where we're going from positive, we have a positive slope, and then we go down to negative, this is a max, local max. And in fact, this is consistent with what would happen if we were to graph this function. I haven't done it, but many of you can probably see in your head what this looks like. This function, it flattens out for just an instant at x equals 0, then goes up to x equals 1, and then we have this function. That's what I'm drawing here is in purple is the x cubed part of the function. And then it becomes 4 minus 3x, which means that the function starts way up there, it comes down, and finally the function just becomes that line. So you can see that there's actually a corner here where clearly the function is not differentiable, because we know that that's what points of non-differentiability look like. On the other hand, at x equals 0, what's going on is the function flattens out like this. So even though the direction of the function is straight horizontal at x equals 0, the function doesn't keep turning to form either a max or a min. It starts out increasing, stops increasing for just a second, and then starts increasing again, so it doesn't actually form a max. That's why we see that the derivative doesn't change sign across this point, so there's no min or max. So let's just summarize our conclusions. We'll say that x equals 0 is not a min or max, and x equals 1 is the location of a local max.